Perfect. So it's my pleasure to introduce Amir. He is going to talk about a lot of work that's on behalf of an academic community as well as corporate community working together on an ML architectural gym. So how do we start to think about how do we create an opportunity where we could actually have AI start to create ML, how we can have AI start to create systems. So with that, Amir. Can we get the slides and the microphone? The slides are there. There we go.
He was Yes. We'll have one with Mike on it.
Cool, thanks. I hope that, okay. Hi everyone, it's great to be here, this amazing crowd. So today I will be talking about Architecture 2.0, a concept that we work with the community to define how we should track machine learning into hardware design and system design. Okay, yep. So my name is Amir. I'm a research scientist at Google DeepMind, and unfortunately, Vijay, my co-presenter, couldn't be here. I hope I can take you with me today through the importance of revisiting and rethinking how we traditionally design hardware and build our systems at the presence of machine learning and machine learning technologies. So to start, I will talk about kind of Architecture 2.0. It's very simple. So I think many people here are familiar with the concept is we want to use machine learning and AI technologies more and more to be able to minimize human intervention throughout the process of system design and hardware design. We also would like to be able to build more complex and more efficient systems. And finally, we would like to reduce the idea to market timeframe. We would like to reiterate through different ideas and different technologies and be able to evaluate them. And we believe machine learning could help us throughout this process. I don't think I need to convince everyone here the revolutionary application of generative AI and machine learning and foundational models in virtually every sector of technology. That's from question answering, generating images, solving puzzles, and everything. However, a critical part, it seems to be missing here. Foundational models have the potential to transform hardware into functional chips. And the potentials here is vast, and it's a lot of opportunities here. That includes hardware verification, code optimization, accelerator design, cloud scheduling, and so on and so forth. And there is a huge opportunity here, but the question that exists here is that, are we ready for this transformation? Highlighting some of the key, so here I'm trying to highlight some of the key challenges that we believe the community needs to think about to fully embrace the potential of machine learning. This list by no means is exhaustive, but we believe it's a good start to bootstrap the integration of machine learning into our platforms. For the rest of the talk, I will take you over each of these challenges and share our vision and what we learned from our discussion with others in the community on what we need to do. So first is about dataset. I don't think anyone argue about the transformative impact on the machine learning through the ImageNet. So ImageNet was a public dataset, is still a challenging dataset for the machine learning community, and one of the key forces that brought the whole community together to make great progress. and all the progress of machine learning, I think we owe it to ImageNet dataset. However, from a system perspective and hardware perspective, we unfortunately don't have a large and high-quality public dataset. I'm not trying to say that there is no dataset, but we still need a dataset that is challenging enough for our community to get together and be able to make progress. In addition to that, there is also a lot of challenges about IP data. We need to make sure that what are the IP data, how we can keep them private if necessary, how we can share it, and so on and so forth. In addition, we need to make sure to strike a safe balance between availability of the data and privacy of the data. There is another challenge here as well. In contrast to machine learning dataset, many of machine learning dataset like ImageNet, as I mentioned, GitHub, YouTube, Common Crawl, and so on and so forth, we unfortunately for the hardware system and for the system design, we cannot just scrape internet to collect the dataset. We need to rely on simulators and to be able to collect some of the dataset, or like actual system evaluation. So most of us are familiar with the cycle accurate simulator. It's slow. It takes maybe weeks or days to simulate a full traces of applications. While on the other end of the spectrum, we have analytical and roofline models, where we trade off accuracy for speed. However, here, establishing a balance between cycle accurate and analytical dataset is very critical for us in many various applications, whether we are building a proxy models, whether we are doing design space exploration, and so on and so forth. So there are nuanced challenges of balancing accuracy and data accessibility that we all need to think about it. I'm not here to give solutions. I'm here to discuss about challenges that exist ahead of us. Next, ML algorithms. In its present state, it appears to be a mishmash of different algorithms and hyperparameter settings. If you look at the papers and publications, everyone talks about different algorithms, different hyperparameters, and different setup, which seems not to be a very systematic evaluation of machine learning progress. To kind of highlight a few is that some of the questions that we need to answer is, which ML algorithm to choose from pool of algorithms for our problem? Which hyperparameter to use? How to compare different ML algorithms in a fair and reproducible way? In addition, ML algorithm landscape is rapidly evolving. So let's talk about some of them: heuristic algorithms, supervised machine learning, unsupervised machine learning, semi-supervised machine learning, and reinforcement learning. Even if we zoom into reinforcement learning, we can see there are various algorithms like policy optimization, value optimization, imitation learning, and so on and so forth. So it is very important for us to be able to evaluate these algorithms in a very systematic way and be able to kind of identify what are the challenges, which algorithm, how and when to use each of these algorithms. Next, let's talk about tools and infrastructure. Throughout the history of computer architecture, we relied heavily on simulation and toolset to innovate and progress. Simplescaler, Pin, and Gem5, and many other tools. Meanwhile, of course, the machine learning community also moved forward by leaps and bounds. As I mentioned, for example, AlexNet, and also OpenAI Gym, which helped us to kind of evaluate RL algorithms and make Atari games and so on and so forth. But the important part is that we are now at a critical juncture, and it's time for another sharp pivot. So buckle up. We are here to harness the potential of machine learning technologies, and especially generative AI, in the service of computer architecture applications. And this is the reason we are championing the concept of Architecture 2.0, aiming to unite the community and encourage collaborative efforts in reimagining conventional hardware and system design. Our goal is to integrate machine learning technologies at the very heart of hardware design, ushering in a new era. So recently, we published a paper in ISCA 2020, this year, 2023, which we introduced open source Gymnasium for ML-assisted architecture design. And the idea was that we want to create a platform for everyone to be able to contribute not only in the ML algorithm landscape, but also be able to kind of use these different ML algorithms and apply it to their system problems. We also published a blog post in the Google research blog post, and we kind of shared more information about this technology. Some of the key learning from this study was, and actually some of them was surprising for us, is that if we look at the pool of machine learning algorithms for different problems in the system, for example, designing a memory controller or designing an accelerator, we generally find out that many machine learning algorithms could be equally favorable in optimizing hardware design to meet user-specified constraints and targets. And this was kind of surprising for us that even random walk, if we give it enough space, it can kind of provide competitive solutions. In addition, we identified throughout this open source Gymnasium, we identified that using diverse data set from different agents, for example, RL, simulated annealing, or Bayesian algorithms, we identified that using different data set and diverse data set can help us to improve the quality of learned proxy models. And finally, ArcGym, this is open source Gymnasium, facilitate the process of developing and integrating different machine learning methods into a variety of architecture simulator. So basically what we did, we created an interface between architecture community, system community, and machine learning community. So it helped us to communicate with the machine learning community and ask them, hey, we have this problem. These are the challenges. These are the parameters. Can you help us to develop the best machine learning algorithm to solve this problem? Next, best practices. So I don't think there is no one-size-fits-all solution for our problem, system problem and hardware problem. It requires us to understand the space really well, whether it is a high dimension or it's a low dimension, whether it is a discrete space, whether it's a continuous space, and so on and so forth. And of course, latency sometimes is very critical in deploying some machine learning solution into a data center, into edge, and so on and so forth. And these are the things that we need to kind of think carefully when we choose our algorithm for solving a problem. Last but not least, also how we deal with the data availability, whether it's a rich data versus low data space, and how we can manage distribution shift that is inherent to many system optimization problems. These are all critical. And these are here, like I listed some of the questions or some of the challenges that we deal with in solving many system solutions. I think to kind of summarize it in one sentence is that it's very challenging and it's very hard to verify and validate many of these ML algorithm solutions. And on top of that, I think in system domain and architecture domain, we are very familiar with interpreting this solution. We would like to understand when we suggest a solution, what is the reason behind it? What is the main contributing factor into this performance? I think there are a lot of questions here that we need to kind of work together and systematically kind of summarize it to be able to progress. Workforce and training. So we discuss about a lot of technology, a lot of questions, and of course the ML landscape, there are different algorithms. One of the key metrics here is that we should be able to kind of train students and train developers and train whoever wants to kind of contribute in this space. And we be able to kind of build a workforce to help us to embrace machine learning. One of the, again, some of the challenges that we thought about it is that, for example, if for ML for computer architecture, what do we need to include in the architecture kind of books or architecture courses for the student to be able to use machine learning algorithm in a productive manner? What are the AI-assisted tools? What are the tools that we need to build that we, like simple scaler, like Gem5, what are the tools that we need to build to be able to facilitate using machine learning into our research, into our products, and so on and so forth. And of course, how we can encourage students to engage in this tool building community. Finally, also training strategies. What are the training that we require to enable machine learning into our workforce? And where are the upscaling or rescaling opportunities in this space? Last but not least, I think it's a very good topic for OCP. It's about industry relations. So there is no doubt that OCP has enabled a rich platform for various sector of companies to work productively together, and to expanding roster of companies is itself ample evidence of OCP's impact. It's very, very useful. And we are confident that Architecture 2.0 initiative will find an ideal home in OCP. We are hoping by joining OCP community, and not only benefit from the wealth of expertise within this community, but also to foster the development of initiative products and enhance the seamless incorporation of machine learning into various technologies. And we have already started to talking with different companies and different academics, and be able to see how we can create work stream and initiate some of these collaborations. And we are very pleased with the positive feedback that so far we have received from different people and different industry. And we are enthusiastic about collaborating with everyone to achieve our shared objective. Okay. So if we want to have an impact, if we want to build and progress in this environment, we have to build a community. And this is the way that we all can achieve collective gains. This is precisely our goal at the beginning of even starting talking about Architecture 2.0. And it reflects the effort that we have been dedicated over the past few months. For example, we started a virtual workshop in September, and it was really great. We have received like attendees. We had attendees from all over the world, and which was very encouraging to us. Personally, it was very shocking to me that see this many universities and academics would like to contribute to this initiative. And we also received support from industry players and national labs. So we are reaching to the end of the talk. So although it may sound cliche here, but the success of Architecture 2.0, and by the way, we are at the beginning of the Architecture 2.0, we have kind of started developing some effort and work stream. But if we want to see the success of Architecture 2.0 concept, it really hinges on our ability to engage everyone's support in various ways. The contribution of numerous individuals, including those listed here, have been indispensable. And our continued progress relies on the support of this dedicated and growing community. So I talked about various challenges and more raised questions rather than giving answers. But if I want to conclude my talk and talk about some of the clear action items that as a community we can do together to make to take the next step for Architecture 2.0, I would like to leave you with this call for actions. I think we need to get together and ensure how we can define some protocols. And I think OCP is a really right place here. So how we can define protocols and standards for the ImageNet-like dataset for our community. What is a good representative dataset that is yet challenging for the community to build? And of course, we would like the companies to contribute to it and be able to kind of, all of us get together and solve this problem. We would like to see how we can create some protocols to collectively contribute to the ML-assisted computer architecture dataset. And finally, how we can kind of collect and share the best practices that everyone uses, like which algorithm to use, which hyperparameters to use, and be able to kind of share it with the rest of the community. I believe, like, for example, some of the initial effort for architecture, ArcGym, would enable this, this effort. I think with that, I now open the floor for open discussion and welcome any questions. Thank you.